Next logical operation to implement is NOT, and the hardware for that is like this. As you see, we have 8 NOT gates, which means that we could abstract it like this. We have an 8-bit NOTer, which would get an 8-bit input A and an 8-bit output, which would always be the complement of this A. You see, we have talked about this logic gate, this NOT logic gate. If you have 0 here, you would have 1, and if you have 1, we would have 0. The instruction which uses the underlying hardware is CMA in 8085 microprocessor. CMA would be 1 byte long, and the opcode for that is 2F or 00101111 in binary. So what it does is that, well, you might say, well, we don't have any operand right now. How does it just executing an instruction? What kind of operand is the one that this complement is instructed on? Well, that is the accumulator. CMA means complement A, or complement the contents in the A register. In other words, whenever we have 0010 ones in the IR register in 8085, what the CPU does is that it first would load the contents in the A register. Imagine the contents in the A register is B6 in hex or 10110110 in binary. It would load this content and put it on these 8 bits, or at the abstraction level would put them in this A input and would calculate the complement of it, and the out would be saved also in the A register again. So in other words, the CMA would complement the contents of the A register. So here imagine that the content of A was this when the CPU encounters the value of 2F in the IR register. This would become 01001001. Now A register would be equal to 4, 8 plus 1, 9, 49 in hex instead of B6. I also want to show you some other circuits. One of them is this, the same AND there, but the second input has been connected to each other. You see this truth table of the AND gate, which is the combination of a NOT in front of a NAND gate. Whenever we have a 0 on one of the inputs, the out would be equal to 0. So I have connected one of the inputs to each other. If this is equal to 0, then it doesn't matter what the other input is, which I want to call it an 8-bit A. The out would always be equal to 0. So I want to abstract this circuit and call it a clear gate. This clear gate would have an 8-bit A or input and an 8-bit output, and it would have one control bit. If this bit is equal to 0, then what this circuit does is that the output would be equal to 8 zeros, ignoring what the input is. Also, you could find out that if the other input is equal to 1, which means this bit, then the output is always whatever the other input is. So you see, when B is 1, the out is equal to A. See, A is 1, when B is 1, out would be always be equal to the other input. So we could say that this circuit, what this does is that if this bit is equal to 0, the out is equal to 0, and if this bit is equal to 1, out would be equal to A. One other circuit that I wanted to show you is this one, which is for comparing. What we want to do is that it is comparing to 0. We want to show you one thing. You see, this circuit has one output, 1-bit output, and 2 8-bit inputs. I have put some XOR gates, which its truth table, you know how it works. When the inputs are equal to each other, the output is 0. Otherwise, the output is equal to 1. Also, you know the NOT gate, and this is an OR gate. For the OR gate, we know that we will have 3 ones here and 0, and the NOT gate is the complement of the input. So at which time the output here is 1, when the input of this NOT gate is equal to 0, right? But when this output or this bit is equal to 0, when all the inputs of the OR gate are equal to 0. Because based on this truth table, if only one of the inputs is equal to 1, the out is equal to 1. The only time that the output of an OR gate is equal to 0 is when all the inputs are equal to 0. So in order for us to have a 0 here, we need to have 8 zeros at the 8 inputs of the OR gate. But these inputs of the OR gate are the output of an XOR gate. Now, when the output of an XOR gate is equal to 0, when both inputs are equal to 1, are equal to each other. When both inputs are equal to each other, then these bits would be equal to 0. And if all of them are equal to each other, then the output of the OR gate is equal to 0, and this NOT would make it 1. In other words, we could say that if these both 8-bit inputs of A and B are completely and exactly like each other, then this out would be equal to 1. Otherwise, this would be equal to 0. Like imagine that we have, for example, two values. All the inputs are equal to each other except one of them. So you know that we would have 0, 1 here, 0, 0, 0, 0, then you would have 1, 1. All the corresponding bits would be compared with each other. We could just use the word compare. Why? Because all of these XOR gates would look at all of these bits. They would all become be equal to 0. When you have two ones based on this truth table, the output would be equal to 0. Only for this one, because we have 0 and 1 based on the truth table, the output would be equal to 1. So we have a 1 here. The OR says if one of the inputs is equal to 1, the output of the OR would be equal to 1, and then this NOT gate would make it equal to 0. So if two inputs are completely like each other, the output would be equal to 1. I abstract it and I say this is for comparing two values. If they are completely equal to each other, the output would be equal to 1. Now, one other thing that I wanted to do is to connect one of the inputs to 0. So these input, I just connect them to 0, all of them, and abstract it like here. The B input is all equal to 0. When the output is equal to 1, when A is also equal to 0. So I call this circuit compared to 0. You see, because one of the inputs is always 0, the only time that the output is equal to 1 is when the other input is also equal to 0. These clear and compare circuits, you'd see how we would use them in the next lecture. So what we are going to do in the next lecture is to now look at the arithmetic implementation of the ALU.